Okay, so welcome to the Friday Theoretical Astrophysics Seminar. It's really a pleasure today to have Michael Tremmel giving the talk. So Michael came from the University of Washington as a PhD student. It's a place that I'm very attached to because it's where I spent some years in the postdoc time, and his advisors were also some of my mentors, Tom Quinn and Fabio Governato. So he taught his PhD in 2017, and then he moved to Yale with the Prize Fellowship, the YCAA Prize Fellowship. And then he stayed on for a few years in Yale because then he got the NSF Fellowship. And so only last year, he moved from Yale with a lecturer position, so permanent faculty position at University College Cork, where he just settled. And so he has worked a lot on simulating massive black holes in galaxies, in cosmological simulating, especially focusing on the low mass galaxies and the feedback effects and also the dynamical evolution of black holes. And so I let you the stage.
Thanks, Lucio. Thanks for having me. It's great to be here. Yeah, so I'll be talking today about massive black holes in cosmological simulations. As I'm sure many of you are aware, simulations of galaxy formation are a super important way in which we can understand the galaxies that we observe, the formation, the origins of galaxies and their properties. But there are certain aspects of simulations that result in certain things being overlooked, or at least not being included or predicted in these simulations, things that we know exist in reality. And so this talk will be focused on maybe the lesser focused on black holes in simulations, black holes in low mass galaxies, dwarf galaxies, and black holes that exist away from the centers of their host galaxy. Things that are typically really difficult to detect, which is why I call them hidden massive black holes, but a population that I think is actually growing in importance in terms of our need to understand them to get a holistic picture of where massive black holes come from, how they affect their galaxies in the universe. Let's click in there. Okay, so just a quick introduction, right? The way we typically detect black holes in galaxies, one way we can do this is dynamically, looking at the centers of galaxies and typically the bulge of, say, bulge-dominated disk galaxy, look at the kinematics of stars and infer the presence of extra mass in the very center, which would be a massive black hole. And of course, we can also detect these black holes when they accrete, when they grow by consuming gas around them. That gas forms accretion disks that become very bright in high energies. We can observe these as active galactic nuclei, quasars, and sometimes very, very bright objects at very early times, like the one I'm showing there. So we can see black holes all throughout cosmic time through their dynamical interactions and as they grow from accreting gas. And of course, we have this nice relationship that we can derive empirically, this relationship between the mass of a black hole and the properties of their host galaxy, which essentially comes down to bigger things have bigger black holes and smaller things have smaller black holes, which is nice, but really is the centerpiece for that drives why we want to understand these black holes in the context of galaxies. Because what this relation means is that somehow these black holes, which are a fraction of the percent of a galaxy's mass and the size at most of a solar system, somehow know about their host galaxy, and somehow the host galaxy knows about them. Right? We know that black holes can drive really powerful outflows in galaxies that can even dwarf the galaxies themselves. So these tiny objects, tiny relatively speaking, objects can have tremendous influence on huge scales much, much larger than their actual sizes. And in fact, could be a really important aspect to galaxy formation theory, maybe involved in how we transition from blue star-forming spiral galaxies to red and dead elliptical galaxies. And so our kind of summary of what we try to do in in this field is understand how this evolution goes on with time. How do galaxies and black holes grow together through time? Is that a purely coeval growth, symbiotic growth, or do you have periods where one is dominating over the other? Is the galaxy kind of holding back gas from the black hole at times? Is the black hole driving gas out of the galaxy, affecting star formation? When do these things occur? And herein lies a big challenge, right, observationally, because we're getting really good at detecting black holes in relatively massive galaxies in the low redshift universe. So this kind of endpoint at this evolutionary cycle, we have that pretty well down. The problem is, as we go to the early universe, as we try to trace these black holes as they were when their galaxies were smaller, when they were smaller at earlier times, it becomes increasingly difficult to actually make those observations, to see these black holes and kind of extract this evolution, right? One way that we're making huge improvements on this observationally is detecting black holes in smaller and smaller galaxies. So there's a growing sample of observed AGN in dwarf galaxies, and just expanding this kind of idea of this relationship between galaxies and black holes, right? As we go to lower mass black holes and lower mass galaxies, finding new ways to measure their mass, even when the galaxy is very active, so moving beyond just these dynamical masses from stars, we see that we might have actually had a bit of a biased view of black holes before. Right? So this plot shows the relationship between black hole mass and stellar mass. The blue points show what you get if you only look at black holes in massive galaxies, massive bulge-dominated disk galaxies or elliptical galaxies, black holes that are measured dynamically from stars. But then if you expand your sample to allow for lower mass black holes growing in galaxies that are actively star forming, that might not be bulge dominated, where you might not be able to measure their mass dynamically from stars, but instead use things like reverberation mapping and things like that to measure their mass, you begin to realize that this relationship might be a bit different, right? So expanding our idea of the demographics of black holes that we study is really important if you want to understand their coevolution with galaxies more generally. We might have a very biased idea if we only focus on the most massive black holes in the most massive galaxies that are kind of done growing in the early universe. Now, with these observations of black holes in low mass galaxies, we also find these interesting guys here, these off-center AGN, black holes that are not at the center of their galaxies. So up until now, we typically observe black holes because we need them to be growing or need them to be dynamically interacting with stars. We see them at the centers of galaxies, but that might not always be the case. And in fact, this population of offset black holes that are growing or at whatever levels, low levels, off center from galaxies, is not just in dwarf galaxies, but kind of all over the place. We see off-center AGN, dual AGN systems where we have black holes that aren't just nice at the centers of galaxies. And so again, we see that we need to maybe expand our view of black holes if we want to get a full picture of their demographics, even at low redshift, and then going further back in time, being able to see smaller black holes and smaller galaxies to really completely understand their properties and therefore their formation. Right? And I think that this is really nicely motivated by recent observations with JWST, right? So already with JWST, we're seeing that we can detect AGN, detect black holes at very high redshift. And these are black holes that are smaller than we've ever seen at such high redshifts, but they're also in small galaxies. So these are relatively low mass black holes in relatively low mass galaxies, and compared to other observations at those redshifts, are growing relatively slowly. And so this plot here shows results from the recent observations from JWST. And you can see this star point is what JWST observed, and the blue and purple points are what we've seen so far. And so you can see that if you only look at the most really, really massive, really rapidly growing quasars, you get a biased picture of the overall black hole population at early times. And if you make your model based on that, you'll have, well, a very biased and incorrect perception of what the typical black hole is doing at high redshift. And this has an effect on kind of our overall picture of how black holes grow in the universe, right? If is similar to the star formation history of the universe. If you think about the black hole accretion history of the universe, as we get better at detecting smaller black holes growing less rapidly, it changes our picture of the overall growth history. So with JWST, we're seeing more typically obscured black holes that we didn't see before, growing at lower accretion rates, that if we calculate this black hole accretion rate density, there's evidence that there's actually a lot more black hole accretion happening at early times than we previously thought. Right, so those data points there represent recent results from JWST, and the lines represent previous estimates of the accretion rate density history of the universe. And so again, being able to see smaller black holes, smaller galaxies, lower accretion rates gives us a fuller picture of black holes. And of course, cosmological simulations are critical in understanding a lot of things about galaxies. They've given us already a ton of information, a ton of new abilities to understand how galaxies evolve, the processes internal and external that affect the evolution of galaxies. Because these simulations are evolving in real time, galaxies within this evolving universe, within the cosmic web, each galaxy having their own environment, own merger history, and all those internal processes happening in real time, really has tremendous predictive power. And they've already done a lot to help us, begin to understand this relationship between black holes and galaxies, right? With all these different simulations that are out there, simulations with different resolutions, different sizes, different physical implementations of, black hole feedback, black hole formation, all that stuff, we can do things like, compare the predictions that these simulations have for the relationship between black holes and galaxies, compare those against each other, against observations, and begin to understand, how is the physics affecting, how black holes grow across time. But by design, and you could argue by necessity, often these simulations are only focused on understanding relatively massive black holes in more massive galaxies, right? So doing things like, trying to understand where the brightest AGN at high redshift come from, where the first really massive black holes exist in the early universe, or how do massive black holes in massive galaxies result in quenching and the formation of giant elliptical galaxies. These are all really important questions that we need to know, but they're all focused on understanding some of the most massive black holes in the most massive galaxies. But all the simulations and observations agree that the majority of the universe is not black holes in giant elliptical galaxies, massive black holes in, really bright quasars or redshift 8. Most of the black holes in the universe are small. Most of the black holes in the universe are low mass black holes in lower mass galaxies. And most of these black holes are missed both in observations and in simulations, though observations are improving, and I'll argue how simulations are improving as well. But all these, what I'm showing here, different mass distribution, mass functions for black holes, from cosmological simulations in the right, or on the left and in the middle, and from semi-analytic models and observations on the right. And again, everything agrees that small black holes are typical. So if you think about trying to understand the physics of black holes, it becomes difficult to say that we can really understand the physics of something when we're only studying kind of the top 1%. To be like trying to understand how typical humans live, if you only study, the richest people in the world, you'll get a very biased and strange result that is not near to truth. So, like I said, in this talk, I'll be talking about two typically ignored populations of black holes in simulations: black holes in dwarf galaxies and off-center black holes. Now, typically in simulations, massive black holes simply don't exist in galaxies. Simulations by hand essentially only place black holes in more massive galaxies. And in terms of wandering black holes, most simulations just assume that black holes always exist at the centers of galaxies and nowhere else. So both of these things are things that are often explicitly excluded from simulations. So it's not that they're failing to do it, it's that they're not trying to do it. The science motivation is different, and that's okay, but it means that we also need simulations that try to understand these things. And that's where the Romulus simulations, the simulations that I use, come into play. Right? So with the Romulus simulations, these are large-scale cosmological simulations. Two different flavors of Romulus I'll be mentioning today. Romulus 25 is a uniform volume 25 megaparsec box, and Romulus C is a zoom-in simulation of a galaxy cluster, about 10 to the 14 solar masses. And with these simulations, the focus was on changing the way we model black holes, trying to remove some of these kind of assumptions that limits the predictions that these simulations can make. So in these simulations, we form black holes in early times based on local gas properties. So we allow black holes to exist in low mass galaxies. We predict where they form. We don't assume where they form. And we allow them to dynamically evolve realistically. We don't require that they're always at the centers of galaxies. Instead, we predict how they move within those galaxies and within galaxy mergers and things like that. I won't be talking too much about black hole feedback, but we also have, the ability to, quench massive galaxies, drive really powerful collimated outflows and things like that. That would be the topic of a whole different talk. So I'm going to start with looking at low mass galaxies. So black holes in small galaxies. These are various observations of galaxies that have been made in different wavelengths. And again, the really importance of understanding black holes in these low mass galaxies comes down to, really just trying to expand this relationship, right? This relationship between galaxies and black holes. How far down the mass scale does this still hold? But as we go down in galaxy mass and towards lower black hole masses, we also begin to be able to constrain where these black holes come from in the first place. Right? That's what makes dwarf galaxies particularly interesting for massive black holes. We don't know where these objects came from. We don't know exactly how they formed and what numbers and in what mass. But as we get to these galaxies that are small, the idea is that these black holes are close to their initial masses, that they haven't had a chance to grow because their galaxies are so small with, really quiet merger histories and things like that. Right. And so we can begin to kind of understand where black holes might fall in terms of these different formation scenarios. Right. So I'm not going to go into the details here, but we kind of have an idea of a few different ways in which we might form massive black holes, ranging from the collapse of a supermassive star, the collapse of a nuclear star cluster, or just, the evolution of early stars. All of these things essentially predict black holes that begin at different masses and at different frequencies, right? And so the number and mass of black holes in these low mass galaxies could help constrain the relative importance of these different formation channels. But of course, the problem, as I mentioned, is that the simulations that we use to try to understand where these black holes come from, how they evolve with their galaxies, testing this idea that are black holes in dwarf galaxies really their seed mass, things like that. These simulations don't include black holes at low masses. Right, this is a plot of the occupation fraction, the fraction of galaxies that host a black hole as a function of their stellar mass. And all these simulations I have up here right now, they all kind of just drop down to zero at dwarf galaxy scales. And that's by design. These simulations are focused on having black holes in massive galaxies, not in dwarfs, and they're often explicitly not even attempting to seed the black holes there. So in Romulus, right, what we do is we just say that any really kind of special region in the universe could form a black hole. Any region that has really, really high densities without any metal enrichment. So then regions where you haven't been enriched by star formation, yet you're attaining very, very high densities. You're collapsing on timescales much shorter than the star formation timescale, much shorter than the cooling timescale at early times. This is where you form black holes. And so in Romulus, without making any assumptions, we have our black hole seeded by about redshift of 5, without making any assumptions about where those black holes might form. Yes? So so we don't make any explicit assumption as to the formation channel, but we do only limit ourselves to black holes that are able to attain high masses. So we don't start black holes off at, say, 100 solar masses. We're only trying to pick out regions that are likely to host a black hole that can reach, 10 to the 6 solar masses relatively quickly, right?
could in principle accrete very rapidly.
Definitely right. But because we don't resolve star formation at redshift 20, we would miss those anyway. So we basically have this kind of fuzzy period in simulation from like redshift 20 to redshift 10 or so that we're not really resolving any star formation just because the spatial resolution is too small. We don't resolve those halos where we just wouldn't be able to really find these black holes forming initially. So what we have to do is at later times say, all right, if I have this region that is really, really dense, this could be a good candidate for a region where either I'm forming or have formed a supermassive star, or if I did have one of these small seeds, it would be able to grow very, very rapidly to be large. Does that make sense? So you're right. We are a little bit not ignoring, but not including these 100 solar mass black holes that might be floating around. We're only including black holes that we think might have a potential to reach, a million solar masses or so, if that makes sense. Okay, so with this formation channel, we form them early, but we also avoid this other issue common in other simulations where you have this prolonged seeding period. So if I have a simulation, say the illustrious simulation, that forms black holes in galaxies above a certain mass, they have just a mass threshold, then what I'll see is that I'll have black holes kind of coming into existence in my simulation all across the history of the universe as halos cross this threshold. So even if I look at somewhat low mass halos in one of those simulations, the black hole might have only kind of popped into existence, cosmically speaking, yesterday. So we avoid that as well. Sorry? Why it's a problem to this? So I would say that all of the current channels of black hole formation, for the most part, except for, as Lucio would tell you, the merger channel, the compression of gas channel, these typical channels here all occur at high redshift, typically redshift greater than 10. And so if I have a black hole in a dwarf galaxy if I can see that galaxy at redshift 1, I'm pretty confident that black hole didn't form at redshift 1.5. And so that black hole has co-evolved with its galaxy from early times in the universe. So if I have a galaxy where the black hole popped into existence at redshift 1, that's missing all that co-evolution of the universe that would have taken place. And I just have a galaxy that I just basically put in by hand that has zero predictive power at that point. I chose to seed a black hole in this galaxy. I place it at the center. It's there now, and it's done nothing because I put it there yesterday. You know what I mean? So I would say, yes, it's unphysical. So the other thing that we get from this method here is a predictive occupation fraction for black holes. Rather than an occupation fraction that's dependent on my assumption as to which galaxy should or shouldn't host a black hole, I now have a way of predicting which galaxy should or should not. And this occupation fraction evolves over time as well. So, and in this plot here, occupation fraction is a function of stellar mass. I'm showing not only how it evolves, but how it compares to some rough observational estimates that I would take with a grain of salt, but without any assumptions or fine tuning, they match the observational predictions quite well. But again, I wouldn't necessarily say that's, super amazing, because I wouldn't necessarily trust those observational predictions to a, large degree. So looking more deeply at these black holes in these low mass galaxies, a former PhD student who's recently graduated, Ray Sharma, was looking more closely at, okay, how many black holes in these low mass galaxies would actually be detectable using current kind of observations, right? Even the observations that can detect black holes even at very low luminosities, how many would we actually see? And he showed that we can actually match the occupation of AGN in dwarf galaxies with observations relatively well. We maybe a bit over prediction of luminous AGN. But if we look at the kind of overall population in terms of the X-ray luminosities we predict for these AGN as a function of their stellar mass, as a function of their host galaxy star formation rate, we actually match the observations quite well. So the colored points here represent Romulus dwarf galaxies with a detectable AGN, an AGN that's more luminous than the detection threshold and is 3 times more luminous than the X-ray luminosity of its host galaxy in terms of the hot gas and X-ray binaries that we'd expect in the host galaxy. And so these observable AGN in Romulus, compared to those crosses and X's, which are the detected AGN in dwarf galaxies, we match quite well this space in terms of X-ray luminosity, stellar mass, and star formation rate. But we also predict that there's a whole population, these grade points here, a whole population of dormant black holes in low mass galaxies, a significant population of black holes that are missed even by these very, very good observations, very sensitive observations to AGN. We're still missing a significant number of these black holes, at least as predicted by Romulus. Yeah. So the majority of them are around 10 to the 6 solar masses. Yeah, that's it. It depends. So the seed mass of the black holes in the simulation are 10 to the 6, and often they've accreted even less than that. So they're often very close to their initial masses. Yeah. Though not always, importantly. And in fact, I'm really glad you said that. If we look at the mass of these black holes as a function of their stellar mass, we can see the effect of black hole feedback. So these plots show on the left here the accreted mass, the total amount of mass each black hole accretes from gas, excluding the formation mass of the black hole and all of its mergers. The total amount of mass of the black hole is accreted over time as a function of stellar mass. The blue points represent dwarf galaxies that are redshift 0 or star forming, isolated and star forming, and the red points are dwarf galaxies that are quenched. And so in this case, low mass galaxies in isolation that are quenched in Romulus tend to have overly massive black holes, or black holes that have grown more than the typical galaxy. They're higher in this accreted mass than average. And if we look on the plot on the right, the total feedback budget of these galaxies, if we look at the total amount of feedback from the black hole relative to the feedback energy from supernova, or that the black hole in these low mass galaxies is essentially contributing about 50% or so of the total feedback budget. So when you have a low mass galaxy with an overly massive black hole that has been able to grow a bit more faster than you'd expect for a galaxy at that mass, it can have an effect on the galaxy. It can actually quench isolated dwarf galaxies. And it's because the feedback, not so much that there's more feedback, but that the feedback is from the black hole and not stars. It's concentrated at the center and more explosive and can affect the gas content much more than supernova. Yeah. Yes. Yeah, so most of them, once they quench, do stop growing for the most part, although you do get kind of this maintenance mode situation where gas wants to come back and the black hole continues to grow and stops it from coming back. But yeah, they reach a point of getting high enough mass that they can drive, say, a particularly powerful feedback event that then decreases star formation. Yeah. Now, this results in a bit of an issue, actually, in the simulation, which is that we predict too many of these dwarf galaxies quench in Romulus. So if we look at the overall quench fraction as a function of stellar mass, that blue line in Romulus compared to observations is much too high at low masses. But this enhanced quench fraction is completely due to the presence of a massive black hole. So if I look at the quench fraction for dwarf galaxies that have a central massive black hole in yellow versus those that have no black hole, those purple points there, the arrows represent bins where we have 0 quenched, it's just an upper limit. We have all of our quenching essentially caused by the presence of a massive black hole. Now, what this says is that as other authors have pointed out recently, that dwarf galaxies might be a really interesting laboratory to constrain our models for black hole feedback. Because clearly in this situation, either we're forming black holes too much, maybe they start off too big and that's the reason, but the overall effect here is that the feedback in these low mass galaxies is too strong. And so this, rather than more massive galaxies, the low mass galaxies might be the place where you can really constrain our models for black holes. Now, we don't just have black holes in isolated dwarf galaxies. The ones I just showed were galaxies that are kind of evolving on their own in the 25 megaparsec volume simulation. We also can resolve dwarf galaxies in dense environments like a galaxy cluster. Now, in a galaxy cluster, you have quenching of dwarf galaxies, but not from the black hole, but from ram pressure stripping, where the gas gets quickly removed from these low mass galaxies. And the majority of these galaxies and their black holes are completely shut off. No star formation in the galaxies, no gas for a black hole to accrete. And yet, if we look at the occupation fraction of black holes in the simulation, again, predicted in the same way, these black holes are forming based on gas in the early universe, that results in an occupation fraction that is enhanced in the cluster environments. So this is occupation fraction as a function of stellar mass. The orange points are for the galaxy cluster dwarf galaxies, and the blue points are for isolated dwarf galaxies. And so what we see is that in the cluster below about 10 to the 9 solar masses, galaxies are about 2 or 3 times more likely to host a black hole than their isolated companions. And so the question is, why in this case is this happening? Well, if we look at the evolution of the occupation fraction as a function of time, what we see is that at high redshift, the two simulations are actually quite similar. But as time goes on the right, in the field, dwarf galaxy occupation fraction consistently decreases over time. While in the cluster, you get this kind of stalled evolution around redshift 2 or 3. And so what's happening here is that in the field, you have a lot of newly forming dwarf galaxies. So you think of any stellar mass here, you have constantly galaxies that are reaching a stellar mass. They're growing over time, while in the cluster, galaxy growth kind of stops. Right, you have this big cluster. The galaxies that are in the cluster by redshift 0 have ceased their growth, a long time ago when they actually fell into the cluster, right? So what's actually happening is that we have this dependence on formation time. If we look at dwarf galaxies in the simulation, early forming dwarf galaxies are more likely to have had the conditions required to form a black hole. And then in our case, that's just these galaxies had very, very dense metal-free gas in the early universe. Those conditions, which are reminiscent of true conditions for forming a massive black hole or growing a seed black hole to high masses, those conditions are met primarily in dwarf galaxies with early formation times. So this plot here, these plots for 2 different mass bands show the occupation fraction as a function of formation time. And in the 2 simulations, there's much more agreement. The difference is that in the cluster, in the orange points, you only have early forming dwarf galaxies. You can't have a late forming dwarf galaxy because that formation of galaxies has been suppressed by the cluster environment. So you have this kind of assembly bias sort of thing, if you will, right? Your dwarf galaxy of a given size is likely to have an earlier formation time dependent on its environment. So for this, we went out to 2 times the Vera radius. So this is all dwarf galaxies within about 2 times the Vera radius of the cluster, or 2 times R200 to be specific. Yeah, which is essentially our zoom region at redshift 0. So okay, with dwarf galaxies, with these simulations, we're able to make a lot of new predictions. We can compare to observations. We can see that we actually do a pretty fair job in comparing to observations. We can make predictions for the occupation fraction of black holes and galaxies. That's critically important because from observations, all we have are, say, the AGN fraction. We need to then convert that to a baseline occupation fraction, which simulations like this can predict for us, including the dependence of that on environment. We also can make an interesting prediction that black hole feedback can be influential to the evolution of dwarf galaxies, which is often ignored in simulations. Now, as I said, right, in these dwarf galaxies, the black holes aren't always at the center producing feedback and quenching star formation. In observations, we often find off-center black holes in low mass galaxies, as well as more massive galaxies. And so the other thing we can look at with Romulus, especially because we have black holes in low mass galaxies, So we imagine the merger history of massive galaxies. They go through a ton of mergers that are minor mergers where those dwarf galaxies have black holes. We can make predictions for where these off-center black holes might come from. So we'll talk about the population of black holes in Romulus that are away from the centers of galaxies. And indeed, observationally, current estimates for, say, populations of black holes in the stripped nuclei of galaxies in galaxy groups, black holes that originated within the centers of galaxies that were then stripped of most of their mass by, say, a central body like a galaxy group. These black holes can represent as much as 30% the total black hole population in the universe. So wandering black holes that are not nice at the centers of galaxies, but are the result of, say, stripped nuclei of galaxies that are merging with other galaxies, can be really important and have been observed in the universe. And with Romulus, because we model the dynamics of black holes, we can actually predict where and when these wandering black holes should occur. So in Romulus, we overcome some limitations of cosmological simulations, in particular the limitation of dynamical interactions of black holes. Right? So as a black hole in one of these cosmological simulations evolves, most of the dynamical friction that black hole should feel from dark matter and from stars is missed. Right? You have limited resolution in your gravity, and you often ignore small scale gravity interactions. And so the dynamics of black holes will be incorrect, right? If I have a black hole in a simulation, as is right here in that cyan line, and I let it go, it will sink, but very, very slowly in the simulation because dynamical friction is not fully resolved. And so one way to overcome this is to say, okay, well, I'm worried that my black holes will be too far away from the center because of this numerical effect. I'm just going to put them at the center. And so typical simulations like Illustris do that. They have a black hole, it's 2 kiloparsecs away from the center. Okay, let's push it towards the center and essentially teleport the black hole immediately to the center of the galaxy. But this has the opposite effect where you lose this evolution of the black hole dynamically. As it experiences dynamical friction, sinks to the center, depending on the properties of the merging galaxies, for example. We want to understand that evolution as well. And so by incorporating a subgrid model that accounts for that missed dynamical friction, we can come with something much more realistic. That blue line there represents the dynamical evolution of a black hole when we attempt to account for what's missed due to resolution effects in the simulation. We get a black hole that sinks on a much more realistic timescale and then stays the center of the galaxy when it's supposed to. And so because of this, our dynamics are also predictive in the simulation. And so when you have galaxies merge, whether or not those black holes will eventually form a binary is now a prediction of the simulation, as well as when they don't. So what we can do is look at the simulation and say, okay, when we form, say, a close pair of black holes that we then, assume merge in the simulation, there's obviously a lot more that goes on small scales that we don't include, but we have black holes that come together to form a close pair in binary. How long does that take to happen? How often do mergers fail to ever form a binary? And then what are the properties of the resulting wandering black holes that come from these mergers where the black holes are left on orbits forever? So what we find, if we look at the total cumulative fraction of black hole pairs that form in the simulation, it's a function of how long those black holes spent on galaxy scale separations, right? So basically, how long were those black holes separated by less than 10 kiloparsecs before they merged? We find that typically mergers actually happen relatively quickly, within 1 billion years or so. But there's a significant population of black hole pairs that form after a significant evolution in the galaxy. And in fact, if you look at black hole pairs that form at low redshift, the majority of these black hole pairs are coming after billions and billions of years of evolution within the same galaxy. So these black holes have existed in the same galaxy for a long time before they finally find each other in the center. And so what's going on to create this sort of different distribution of dynamical evolution of black holes? So we can look at two kind of typical situations that happen. So top case is a merger of 2 galaxies that result in a quickly forming black hole pair. So again, we don't follow the evolution of black hole binaries. So when the black holes get close, we assume that they're just one object, ignoring all the complicated binary evolution within there. And then we have this case where a black hole evolves for a couple billion years before actually reaching the center. In this case, it actually hasn't even yet reached the center of the galaxy at the end. These mergers occur at the same time in the simulation and have very similar mass galaxies, but the difference is that up here, this galaxy is intact. You have two galaxies that are interacting. It's the galaxies that are bringing the black holes together through these interactions, sapping away the angular momentum of the galaxies that then can bring the black holes together at the center. But if you have a galaxy that's not quite that dense, that galaxy can become disrupted early on in the interaction, leaving you with kind of a naked black hole in your simulation that wanders around for a long time, because dynamical friction actually isn't that great at taking a black hole from, say, a few kiloparsecs down to the center. It takes a few billion years to do that at least. And so just to illustrate this in an extreme case, here's a forming Milky Way galaxy, and there's this little black hole and this little puffy red galaxy down here. And what we're going to see is this little puffy red galaxy, because the mass ratio is so extreme and its density is so low, it will, all the stars in that galaxy will become tidally disrupted very quickly through this first pass. And we'll see that that black hole is just, essentially going to be in this stripped remnant and will never make it to the center, because there's no real way to lose its orbital energy and sink. So the result of these interactions, these minor mergers that result in very long-lived wandering black holes, are that Milky Way galaxies in the simulation have roughly 5 or so black holes in them. Not just one central black hole, but several black holes in them. And that the number of these black holes doesn't really matter, doesn't really care about the morphology or recent merger history of the galaxy, because most of these black holes were put into the halo at early times. These were earlier minor mergers that took place. The galaxy got stripped, the black holes were placed on these orbits, and dynamical friction is too inefficient to bring them to the center. So we wanted to look at more generally at this population of wandering black holes in galaxies, right? Because as we go to more mass, we'd expect more massive objects to have more rich merger histories, and so therefore maybe more wandering black holes. And indeed, that's exactly what we find. So Angelo Ricarte, who was a Yale grad student, who's now a postdoc at CFA, he looked at this more broadly and found that indeed there's this relationship between the number of wandering black holes in the galaxy and the mass of the halo that the galaxy is in. So if you're in, say, a Milky Way mass galaxy, you maybe have a few, but as you go to group or cluster scales, now you're looking at, hundreds, thousands of these black holes wandering around your halo, not in any galaxy, but just on their own. And if we look at the total mass that is encompassed in these wandering black holes, we find something pretty interesting. So if we look at redshift 0 and we look at the total accreted mass that these black holes have accreted over their whole lifetime, the black points here represent central black holes in galaxies, and the color points represent off-center black holes. And so at redshift 0, the central black holes dominate, which isn't surprising. Those are the black holes that have, all the fuel, all the gas around them to grow. They'll grow much more rapidly, and these wandering black holes will be stunted very early on, and so they'll dominate. But as we go to higher redshift, where you have more wandering black holes that haven't yet had a chance to make it to the center, you have more galaxy mergers that are putting them into halos, suddenly they make a significant contribution. So at, say, redshift 2 even, the contribution of accreted mass that exists within off-center black holes is significant compared to the central black holes. So in terms of the overall sort of mass budget, wandering black holes can be significant, particularly at high redshift, when the central black holes haven't had a chance to grow significantly yet, and also you have a lot of wanderers that haven't yet been able to make it to the centers of galaxies. And so one question, of course, is can we actually detect these off-center wandering black holes, right? As I just said, they mostly have their growth stunted, so they don't have a lot of accretion going on. And so it's probably hard to see them observationally, but it turns out that over time, every so often, some of these black holes do become luminous. They find some gas and they accrete at relatively low luminosities. And so this is an example of one such galaxy with a lot of black holes. It's a more massive galaxy, and a few of those black holes are actually producing a significant amount of X-ray luminosity. And if we look at the distribution of massive black holes in our simulation that have X-ray luminosities that are actually detectable, greater than 10 to the 42 ergs per second for bolometric luminosity, we find that we actually match pretty well the spatial distribution of hyperluminous X-ray sources. So these are X-ray point sources that are typically too luminous to be explained by your typical X-ray binary. But in this case, we're saying they could, in fact, be massive black holes that are accreting. So if we look at the spatial distribution of these bright wandering black holes and compare it to the spatial distribution of these hyperluminous X-ray sources, we get something that's pretty darn close to the observation. So it could be that we're already seeing some of these wandering black holes, and we're seeing them as hyperluminous X-ray sources. So I'm coming to the end of my time, but I want to quickly go over some future work that I've been doing, in particular in collaboration with Lutro and Pedro here in Zurich. So wandering black holes, super cool. And again, a new type of black hole that might be really important. Again, if we care about understanding black holes holistically, wanting to understand the total population, these black holes might be a significant part of that population. But again, in terms of understanding black holes in the whole population, as I've already mentioned, recently, we've been detecting galaxies and black holes at very early times. So there's already been some nice work by my colleague, Ben Keller, trying to see if we can explain some of these massive galaxies at early times that JWST is seeing. And it turns out, yes, we can. All sorts of cosmological simulations have done this, as well as some high resolution, high redshift simulations of the universe more recently have shown this as well. So cosmological simulations can explain these massive galaxies at early times, but we don't just have galaxies at early times to think about. We also have these black holes at early times to think about. And it turns out, right, you might naively think that if I see a black hole at very, very early times, redshift 9 in this case, that'll tell me something about seed black holes. But it turns out even observing a black hole at redshift 9, you're still very, very much open to different formation channels, different accretion rate channels. We can explain such a black hole with a direct collapse, a massive black hole that grows at Eddington. We can also explain it with certain super Eddington accretion histories. And so we have this problem where we're trying our best to observe black holes at the earliest times, at the lowest masses we can, and yet we're still coming up with, it's really hard to trace that back to their initial mass, to their initial conditions. And so one way around this, of course, is with gravitational waves. Right? LISA, I don't think I have to spend too much time talking about this here, but LISA is going to kind of revolutionize this. If you think about what black holes LISA will be able to detect, it's going to be able to detect black holes in the era of when we expect them to be forming in the universe in the first place. So it'll be able to detect black holes very close to their initial masses and give us an idea of the overall distribution of black hole masses at very early times, which will be super exciting. But the challenge here is that the formation of a black hole binary and a black hole merger has a lot of scales involved, right? We have to go from halo scales, like hundreds of kiloparsecs, down to galaxy scales, and then the galaxies have to merge, and the black holes have to dynamically evolve there, and then they form a binary that has to itself harden over time to form a black hole merger. And as I've already kind of shown here, this part, going from halo merger to galaxy merger to black hole binary, lots of complicated things can happen there. And in fact, we find, and I'm not going to spend too much time on this, I'm running out of time, but we find if we use Romulus and we use what we find in terms of these delay times to forming a binary with these galaxy scale dynamical evolution timescales we predict, it significantly affects our predictions for LISA results, for how many mergers LISA should detect. But LISA will be the best at detecting the highest redshift mergers from small black holes in small galaxies, and that requires high resolution, right? And we already see in simulations that resolution matters a lot. The more you resolve small galaxies, the more mergers you predict in your simulation, right? If you don't resolve tiny galaxies at high redshift, you just will miss a bunch of mergers, and well, you'll just make a wrong prediction. So we really need high resolution picture of high redshift mergers. And so with Lucho and Pedro, I've been working on taking some mergers at high redshift that we see in Romulus and converting them to much higher resolution, right? And I just want to point out, in cosmological simulations, large-scale simulations, on the left there, that's what we mean when we say a dwarf galaxy merger. So if you have a simulation, even Romulus, which I think Romulus is great, but if I try to make a prediction for the properties and the galaxy properties for where black hole mergers are happening at redshift 4.5, that's the kind of resolution I have, blobs, basically. I can say there's a galaxy and a black hole there, but they're blobs. So we need to go to higher resolution to actually see the structure and evolution of these galaxies, to get an idea of where these binaries are evolving. And that's what we're doing, running a whole bunch of these simulations of dwarf mergers, changing the physics up, changing the merger histories of the galaxies, and doing cool experiments there. So I strategically will leave you with this cool movie playing in the background while I take your questions, and thank you for your time.
A couple of things. One is about your dynamical friction implementation. Do you consider only the black hole, or do you consider also some bound mass around the black hole in case there's some, I mean, what do you do?
That's a good question, and we only consider the black hole mass. That's actually part of the reason why I think a major weakness in Romulus is that we seed the black holes at 10 to the 6 solar masses. And that choice was not made for a nice reason. It was made because we need to resolve the dynamics, and in order to get correct dynamics, the mass of our object has to be more massive than our resolution limit by a significant amount, by at least a factor of a few. So I think that might actually have an effect on like the dwarf galaxies that I showed. We have a black hole that's probably at least a factor of a few too massive than we'd expect for galaxies of that size. It might be growing too efficiently and producing too much feedback. So we don't do that. It is something that I would be interested in implementing, because I do agree that that could be something. Even if you have a 10 to the 5 solar mass black hole, it could exist in the center of a dense cluster, which would essentially give it additional dynamical mass when you're calculating dynamical friction. So yeah, we haven't implemented that. The Astrid simulations have done something similar to that, in part because of necessity, but you can, justify it in that way.
That's an easy way to quantify how different your results would be in terms of the friction feedback if you see the mass.
That's a good point. That's a good question, I should say. In terms of the dynamics, we tested this with the wandering black holes in the Milky Ways, and we said, okay, well, if we had these black holes, they're at these orbits. If they had significantly less mass, it would actually make it even more wanderers, maybe. It would be even worse at getting to the center. Even if they had 10 times more mass, even if there was some unresolved star cluster around them, they would still have dynamical friction times longer than the Hubble time. So the wandering results, I think, are relatively stable for that. I would say that, excuse me. I would say that, that in terms of the accretion history, we find something interesting. So, and I don't have the plots here, but Angelo Ricarte in a paper showed that the accretion rate of a black hole is actually most sensitive to the star formation rate of the galaxy. So the black holes actually nicely follow the galaxy star formation rate, even down to low masses. And so if I have a black hole that's, accreting mass at some rate, it cares much more about the gas supply than about its mass. The mass is a secondary term in that. So I would argue that at least in the model of and resolution of Romulus, we'd be less sensitive to the mass and more to just the gas supply. Most of these black holes are supply limited, I think. Yeah, now that said, we would have a lower Eddington limit if we had lower mass black holes. So there's another factor in there I haven't considered there, but yeah. Yeah.
Or black hole binary.
Mhm.
Would you suggest like a way to target those searches based on like if the dwarfs are clustered or not, or the binary? I mean, you don't resolve the binary evolution after the pair, but it happens and more likely to other that.
Yeah, so I actually have some collaborators at Bishop's University in Canada. So an undergraduate student and his advisor John Runn and I have looked into this. So the student ran some essentially mock observations of galaxies that would have essentially a binary in them that just went through a simulated merger that would likely have an active binary in them to quantify how their properties were different. And I don't want to say the results off the top of my head because I don't want to get it wrong, but there'll be a paper out on that somewhat soon, hopefully, to look at the the differences in things like Gini coefficient and stuff like that about galaxies more or less likely to host a binary. So the idea of finding low luminosity AGN in low mass galaxies is something, people like Amy Raines are doing that all the time. There's work by like Mar Mezcua has been focused on even kind of going to higher redshifts. So some of their results are redshift 1, redshift 2 low mass galaxies, which I think is really cool. So yeah, as we get better, X-ray observations, that'll be super useful. And then even finding dual AGN is becoming better and better over time as we're getting better at parsing out those observations. X-rays can be really hard because there's not a lot of photons there, but.
And I thought it was curious when you said that the typical Milky Way galaxy has 5 wandering black holes, and I presume the mass is at least 10 to the 6 because that's what the mass of the
by design.
Is there a distribution to this number? Is the Milky Way an outlier, or am I missing something?
So there is a distribution, as I showed that. There is a distribution of number of wanderers. We have some Milky Ways with no wanderers, and some, again, Milky Way is defined here based on mass. But I would say that I don't think we can really tell for sure right now if there are maybe a wandering black hole in the Milky Way. Now, again, these are 10 to the 6 because we put them as 10 to the 6. In real life, they could be 10 to the 5 or something like that. And so the question becomes, would we expect these black holes to have some kind of nuclear star cluster around them still or not? That's an open question. So one of the things I kind of find the most exciting is some work several years ago now using Gaia data, looking at streams and finding these interesting breaks and spurs in streams. And they estimate what kind of size and mass of object would you need to create one of these kind of gaps in these stellar streams. And essentially it's something that's like 10 to the 6 solar masses that's smaller than a globular cluster. And nothing, the idea in the paper was, this could be dark halos that are very dense. Could also be a black hole. I don't know. So there's ways. I think better would be kind of broader observations. So I have it as an extra slide I can show. But in theory, that's not it. So we look. Oh, you can't see it. Here, let me bring it over. In theory, if we do some X-ray stacking analysis, so we looked at the galaxies and we said, okay, if we stack the X-ray emission from galaxies in different mass bins, what would be the expected X-ray profile that we'd get if we include black holes? And what would it be if we don't include the black holes, just say X-ray binaries and gas? And so the solid lines represent the prediction directly from the simulation with the wandering black holes, and the dashed lines would be the result without black holes, so all the other sources. And it turns out that around halo masses of 10 to the 11 to 10 to the 13, you do get a signal that there's enough active wanderers that you'd get, say, an enhanced X-ray luminosity at large distances if you stack that data. So that was I guess maybe I should keep this slide in the talk. I think it's actually an important prediction here. It's just a little bit complicated to talk about. So things like that I think could be a really great way to kind of constrain these things. But it's hard. And of course the hyperluminous X-ray sources, we don't see any of those in the Milky Way, but again, it might not be that the Milky Way is an outlier. It's just that these black holes aren't active all the time. And so it's, unlikely to see, if you have a sample of 5, it's likely that all of them are dormant. I hope that answers your question. Maybe that was too much.
So I think, it's super interesting, linking what you have with like you mentioned that you want use some higher resolution simulations. So we're actually running them right now, which is also a good idea. But what I'm more worried about than the solution is the model. Right? And I think this is essentially one specific model for seeding, for feedback, for everything, for growth. I think it would be nice if you could show, I'm sure you have it, right? Like, how does, for instance, the AGN with the master function look like in terms of wind pebbles observation? Does this match? I mean, if you have other observational, let's say points of comparison that would raise the confidence in this specific model, or maybe you could alternatively have thought about exploring, let's say, the parameter space a bit more thoroughly, and so that you get a better understanding of the
Yeah, no, I think that's a totally good point. And I would in general not want to say do things like, Romulus predicts that we should have 10 mergers per year from Lisa. I don't think we can do that. I don't think we're at that point. I don't have the plots in this talk, but I will say we do have too many low luminosity AGN at both low and high redshift. So that's a common problem. We have the same problem as all the other simulations where we have too many low luminosity AGN. And so the issue though with AGN functions, as you know, I think it's really actually hard to make that observational comparison with simulations because you have to essentially convert something that is some average accretion rates over some amount of time to some X-ray luminosity, things like obscuration and stuff. So at the low luminosity end, which is all we can do in Romulus because we don't have very massive galaxies, the observations I think are highly uncertain as well. So I don't really think we have a good way to say this model is right. And I think that's also part of the issue here, right? Is like, as we focus on trying to compare to like super bright AGN in high mass galaxies, it's really difficult to directly compare those observations. And there's plenty of different pathways to get there, just like there's plenty of different pathways to get to the stellar mass halo mass relation, things like that. And so we need to find constraining things that we can actually, do. And that's why I think things like, dwarf galaxy quenching and stuff like that, like I think that we don't match observations in terms of dwarf galaxies. And I think that that's really interesting and could be a really interesting way to move forward. But it's hard to compare it to other models that don't include dwarf galaxy black holes. And so as we get to, studying these more and more simulations, I hope that we can get that. But yeah, I would say I wouldn't trust our model as a end all be all to predict, this is the mass function of massive black holes, or this is the luminosity function, or this is the merger rate. All we can do is, look at the physics, what causes black holes to merge quickly or slowly, what, things like that. That's where I stand on that. I hope that makes sense. Yeah.
It's actually pretty honest.
Okay.
I have a little bit more out there.
Okay.
Presumably, if there were 5 wandering supermassive black holes in the Milky Way, they would have been active at some point. And I'm thinking there's, for example, evidence of supernovas in geological sediments in the Earth. And because the radiation from supernova can deposit some heavy elements that are overabundant with respect to others.
Okay.
Super out there, but I wonder if maybe in the geological record of the Earth there might be some trace of an activation of one of these wandering supermassive black holes.
Oh, like as in like similar to a supernova, if one of these
Yeah.
became active by growing. Oh, I have no idea. I have absolutely no idea. I don't think I could.
They found evidence of supernova.
Yeah, I actually didn't even know that. That's really cool. So it's not like the chemical thing. It's purely just the radiation. Oh, okay. So yes. Okay. So it's the idea that the material came from supernova. Okay. Yeah. But the idea is that the material comes from like the outflows from supernova. Is that right?
It's basically means that the supernova polluted the environment.
Right. So I would say in that case, then no, because the black holes, the origins of them don't, in typical black holes don't really go through supernova, or at least not very strong supernova explosions, not like neutron stars. They often directly collapse or nearly so. In the massive black holes in particular, all of our formation ideas would involve a near direct collapse into a black hole without really a supernova.
Yes.
Oh, I see. Oh, well, then I revoke that and go back to my original idea that I have no idea. So.
Yes.
The thing you said that LIDAR rates maybe overpredicting by 2 or 3 times. Is it because in Romulus the black holes are merging in 2 billion years, and when they calculate rate in LIDAR, they are always the center? Or is it...
Do you mean? Sorry, let me go back to it. So do you mean? You mean this figure here? So yeah, this is the idea. So this is all from a semi-analytic model. So yeah, you have to go from halo merger to when you form a binary and things like that. And so there's different prescriptions in there for the dynamical evolution of the galaxies and then the black holes. And so what we did in this case is add on this kind of galaxy scale kiloparsec evolution. So we have right now the models kind of go from here. If you think about this here, they kind of do this first part, and then they kind of do this part. And a little bit of this, but only at like 100 parsec scales or so, maybe a kiloparsec. And so what we did is we fill that in from like, okay, galaxies started to merge, 10 kiloparsecs or so. What's the typical time scale given the properties of the galaxies that we expect the black holes to reach the center based on what we've seen in Romulus? And so that's where we get so that additional time scale, that few billion years, is enough to either move mergers to lower redshift, and in some cases just remove them entirely. Does that make sense? Thanks.